All right, Math 2, here we go. We got lesson 9.3.3, Piecewise Defined Functions. All right, so the Horizon Phone Company offers a basic monthly voice plan where customers pay low monthly fees, but they have to pay extra if their calls exceed the maximum number of minutes. I guess this is like a throwback question because I don't think phone plans do this anymore. But anyways, how many minutes are included in the monthly fee? Okay, so here we have at $40, it goes from 0 up to $4.50. So that means the price stays the same until we get to 450 minutes. So that means that 450 minutes are included in that $40 monthly fee. So for the first part, we can say that 450 minutes are included in that fee. What is the charge for extra minutes? Okay, so here this is 450, this is 452, this must be 451 right here. So up until 450, we're still $40, and then the price jumps, and this is 41, so this must be $41.50. So the price jumps there for a minute. So for this minute right here, it looks like it costs 50 cents per extra minute. So we're going to say 50 cents per minute. Write an equation for the first piece of the graph. So this is a horizontal line going through 40 on the y-axis. So that equation would be y is equal to 40. The domain would be, these are our possible x values. We can do 0 minutes and up to 450 minutes. That would be our domain. So our domain for this, 0 would work. I could be equal to 0. And I can go all the way up to 450 minutes. After 450 minutes, then we know that the price jumps up to $40.50. All right, write the equations for the second and third pieces of the graph. So this piece, and this piece. So this piece is at $40.50. So that's the equation y equals 40.5. And then the domain for that is from 450 minutes to 451 minutes. So our domain for this one would be from 450 less than, I'm not going to put equal to because equal to was $40. That's what the closed dot mean. Opens dot means that 450 is not included in this price. And then it's going to go all the way up to and include 451 minutes. And then the third row here would be y equals $41. And that goes from 451 minutes up to 452 minutes. So remember, 451 was part of the last price. So we're just going to do less than because it can't be equal to that. And then less than or equal to 452 minutes. So if we want to do this as a piecewise function, this is what a piecewise function would look like. Maybe we'd say something like f of x equals. And then since this graph changes constantly, we'd have to say what's the equation here and when does it act like that. So the equation here was f of x is equal to 40. So that's the equation, but that's the equation only between these domain values. So over here we'd say 0 less than or equal to x less than or equal to 450. Okay, once we get to 450, it changes. The new equation is $40.50. And that's from 451 less than x less than or equal to 450. Oh, dang it, did wrong. This is 50 and this is 451. All right, so 450 stops here and this one picks up right where that one left off. And then our last one that we just got done doing was $41. It started at 451, but it wasn't included, so I'm not going to put the equal to. And then it went all the way up to 452. And it looks like every extra minute we would increase the price by 50 cents. So that is a piecewise function. where you've got several different equations for the same function, and they just changed based on the domain. So here we've got this one. So we've got f of x equals 3. So that's a horizontal line going through 3 on the y-axis, but it only behaves like that between -4 and -2. So let's find 3. 1, 2, 3. So when does it behave like 3? Well, here's -4, so right here, and here's -2. So only from here to here on the x-axis would it behave like this function. So let's see, 1, 2, 3. So it can include -4, so I'm going to leave a closed dot there. And it can include -2, so I'm going to leave a closed dot there. So that's what our function looks like from -4 to -2. Next, the graph changes between -2 and +2. Now notice here it doesn't say that -2 is included because it's just less than. So when I go down here at -2, I'm going to put an open circle to show that that is not part of the solution down here. But then we're going to go all the way to +2, and +2 is part of the solution. So I put a closed circle. So this graph so far, at -4, we're up here. At -3, we're up here. At -2, we're up here. After -2, but not including -2, our graph moves down to here. Once we get to 2, it looks like we jump to 5, and that goes from 2 to 5. So 5 would be up 1, 2, 3, 4, 5. It's not including 5, or not including this x value of 2. And then it's going to go all the way to 5. So 3, 4, 5, and end there. So we've got 3 different parts of the function that are 3 different little horizontal lines, and they all behave depending on what their domain is. -4 to -2, that's y equals 3. -2 to 2, that's y equals -1. 2 to 5, that's y equals 5 up there. Okay, let's do that for this one. So for this one, we've got a line right here, and then we've got a quadratic right here. So the dividing line between these, and you don't actually have to do this line here, but the dividing line between these is that x is equal to 1. So there's where x equals 1 is, right there. So on this side of the graph over here, we're going to behave like the line. On this side of the graph, we're going to behave like a quadratic function, a U shape. Okay, so this one is equal to, so let's go ahead and do this one. So my y-intercept's at -5, so I'm going to go down 1, 2, 3, 4, 5. My slope is 2, so I'm going to go up 1, 2, and over 1. And I am going to put a closed circle right there because I can be equal to 1. So far, here's what my graph looks like. I guess I should put another point down here, huh? There we go. So far, I've got a line that gets to this x is equal to 1 and stops, because this only works when x is less than or equal to 1. Okay, now we're going to do the quadratic. Looks like the y-intercept is at 3, 1. So I'm going to go 1, 2, 3, and up 1. It looks like the a value is 1, so it's the same thing as the parent function. So I would go up, over 1, up 1, over 2, and up 1, 2, 3, 4. Now over here, I can't put a dot because it can't be equal to 1. So this is an x value of 1. So I'm going to put an open dot right there, because this particular function does not operate when the x value is 1. And there's our new function. So on half the graph, it's a line. On the other half of the graph, it is a quadratic. It's a line when we're less than 1 on the x-axis, and it's a quadratic when we're greater than 1 on the y-axis. Flip it over. Valencia is training for a 5-mile fun run. One day she runs from her house to her friend Mason's house 2 miles away. Valencia talks to Mason for 10 minutes while she stretches, and then she runs home. Valencia runs at a pace of 1 mile in 10 minutes on the way to Mason's house. On the way home, she is tired, so she runs at a pace of 1 mile in 12 minutes. Draw a graph of the situation. We can do that. Let's do it. All right, so here's my x-axis over here. And here's my y-axis over here. All right, I'm going to do 1, 2, 3. There's 1 mile, 1, 2, 3, 2 miles. All right, so this is going to be in miles, distance in miles. Sweet. All right, so then we're going to look at the time in minutes for my other axis. So this is going to be time in minutes. Got to really think about my scale for this graph because it looks like we're going to be running. We're going to stand around for 10 minutes. It looks like we're going to do 1 mile every 10 minutes. So let's do everything by 2. So this would be 2, 4, 6, 8, 10, 12, 14, 16, 20, 24, 28, 32, 36, 40, 44, 48. All right, this has got to be enough. Let's 52. I think that should be enough. All right, so when Valencia starts running, that's at time 0. Her distance is also 0. As it says, when she starts running, she's going to go at a pace of 1 mile in 10 minutes. So 10 minutes is right here, and she's going to go 1 mile. Now remember, she's going to go 2 miles to Mason's house. So I went 10 minutes, 1 mile. I'm going to go another 10 minutes and do the second mile. So there's her pace as she's going to Mason's house. Now, according to the problem, she stays at Mason's house for a time and she stretches for 10 minutes. So as she's sitting there stretching for 10 minutes, time goes by, but the distance doesn't change. So for 10 minutes, so up to time 30 at this point, that's what happens. She just stays in the same spot. Lastly, she heads home, but then they're doing 1 mile every 12 minutes. So 1 mile is right here, and then 12 minutes. I'm at 30 minutes right here, so I'm going to go over to 42 minutes. That would be right about here-ish. And then 42 plus 12 more minutes would be 54 minutes. So 52, 50, oh, barely made it. All right, there's our graph. Goes to Mason's house, stays there 10 minutes, comes back. Should the graph be discrete or continuous? So I made mine continuous. Discrete graphs are just points. But we wouldn't do points because that would mean that she's teleporting. This is saying that she's always somewhere along that path. If we just put points, it means that she just magically disappears and reappears in different places, teleporting. And we can't do that yet. So this is continuous graph. All right, write a piecewise function for the situation. All right, so our piecewise function for this one, I'm going to say f of x equals, and the really pretty doodly, I don't know what that is. It's something. So at first, my y-intercept is 0, and my slope is up 1 over 10. So my slope is 1/10. I went up 1 over 10. And my y-intercept was 0, so just 1/10 of x. And we do that from 0 minutes until 20 minutes. So the domain for this one is 0 less than or equal to x less than or equal to 20 minutes. So for the first 20 minutes, this is our path, this is our equation. And then we stay in one place at a time. So this is y equals 2. So f of x equals 2. So this is a flat portion of our graph, and that's from 20 minutes to 30 minutes. So from 20 minutes to 30 minutes, our graph is just a horizontal line because we're not doing any movement. Last part of our graph, we're going down 1 and over 12. So for every mile, we're going 12 miles. So we're going to say negative 1/12 x. And we've got a little bit of a problem here. We don't have our y-intercept. I mean, I guess we could follow this up and try to find the y-intercept, but let's just go ahead and calculate it. Remember, this is a linear equation, which is in the form of y equals mx plus b. We've got a point from our linear equation over here. This point was 54:0. At 54 minutes, we were back home from this line right there. Now, we know that the slope was negative 1/12. The x is 54 because you can plug in any point to the x and y from the line. Put 54 right there plus b. And the y is 0. Okay, negative 1/12 times 54. That's just negative 54 over 12. I think we should be able to reduce that. Yeah, 6 goes into both of those. Goes into here twice, goes in here 9 times. So we get 0 equals negative 9/2 plus b. So I would add 9/2 to both sides, and the y-intercept looks like is 9 over 2, or 4.5, however you want to do it. And then it behaves like that from 30 minutes to 54 minutes over here. So 30 minutes, less than or equal to x, less than or equal to 54 minutes. And there is our piecewise function. Have a wonderful day. Math hard. See you later. Bye.